The next component to install in our little circuit we've been working on is a diode, and this is what a typical diode looks like. Although some of the high-powered diodes look like this. The function of a diode is to change AC to DC. You can check out my video Alternating Current, or AC Basics, to get an idea about AC if you haven't already seen it. I'll be using this diode in the circuit, and it's typical. The faint black mark on the left next to the red nub is the cathode marker. It's important to know which leads are which so you can put the component in the correct orientation. Otherwise, your component may be destroyed. The schematic symbol for a diode looks like this. I've marked the leads and polarity of the diode. Now, this is how it works. We have a model of a diode here. We have the leads marked as cathode and anode. We have a blue side marked N with a bunch of dashes in it. Then a depletion zone with circles and dashes. Then a purple side marked P with circles in it. We also see our marker on the left side called the cathode marker. In the upper left corner we see the dash that represents an electron and an O that represents something called a hole or electron acceptor. You see that the cathode is hooked to the negative side of the battery, so the negative side of the battery is hooked to the N material, and the anode is hooked to the positive side of the battery. So the positive side of the battery is hooked to the P material. Check out the schematic symbol and the polarity, plus sign of the cathode and minus sign for the anode. They match the battery polarity. On the blue side we see electrons. The N-type and P-type materials are substances called semiconductors. Silicon is a semiconductor that we can dope or add impurities of another semiconductor like arsenic, phosphorus, or antimony to increase the number of available electrons in the semiconductor N-type layer. On the purple side, we have silicon doped with semiconductor materials such as aluminum, boron, and gallium, which allows for there to be more electron acceptors, or holes. This is P-type material. Doing this allows the desired control of the flow of current through the diode. Without getting too detailed with the chemistry, we'll just go with the electrons in the N region are not very active when there is no voltage applied to the circuit. Once you apply voltage, electrons flow. Remember that electron flow is current flow and actually goes from negative to positive, not the conventional way, positive to negative, but the true way. So they build up in the N material, but because of the PN junction where the depletion zone is, there is resistance against letting the electrons through. But once the voltage reaches a certain point, which is 0.7 volts typically for silicon, and 3.3 volts, that's 0.3 volts for germanium, current will start to flow. The electrons in the N-type material are migrating across to the other side, filling the holes in the P-type material, and then flow to the load, and then to the bottom, the positive, and then to the positive side of the battery. We call this biasing, and in this circuit, it's forward biasing, which, with the electrons on one side and electron acceptors on the other, current will flow. It's kind of like a switch. At 0.07 volts, the switch is on. Below 0.07 volts, it's off. Another way to hook it up is reverse biasing. Take a look at the schematic diagram and the battery. the polarities are not matched. You have electrons filling the holes in the P material, but once they are full, they are against the N material that is also full of electrons. So the electrons can't get through from either side of the depletion zone. The depletion zone widens as the holes fill with electrons that can't get through the N material. It works kind of like a wall because like charges repel. In this case, all those electrons on both sides of the depletion zone resist current flow. The diode now looks somewhat like a capacitor, and capacitors block DC. So now I've went from a switch to an open circuit. This is how it looks on an oscilloscope. Notice the voltage is on the center line at 0 volts. That was all working with DC. What happens if we throw in AC? Notice we threw out the battery at the bottom and put in a circle with a squiggly line in it, kind of a sine wave looking thing, and call it an AC source. Notice the schematic symbol's polarity on the diode schematic matches the AC supply's schematic polarity. This is forward biased, so the current flows. We're back to another switch. So when the current flows back, remember AC goes forward and then backward, positive and negative. So when the current flows back, or negative, we have a situation that looks just like the reverse bias on the DC circuit. So no current is flowing. Let's review AC a little bit. Remember, if we cycle through an AC current that starts at 0 volts, going to the positive direction, it builds upwards on the oscilloscope to a maximum, then drops down to 0, flowing in one direction. It then builds back up to its maximum voltage again, but flowing in the opposite direction. It's still voltage and current flowing, but on an oscilloscope, we see it as dropping below the center line, indicating it is going in the opposite or negative direction. One cycle consists of completely going through both directions or reaching the center or 0 line 3 times. Start, the second one, and then the final one. If starting at the 0 line, it looks like this. But when you install a diode, you get a voltage in one direction, but not the other. It looks like this. Notice on the forward biased AC cycle, you get current flow, the arc above the center line, but not on the negative biased AC cycle. You only get the center line or 0 line. So you're missing the negative direction. Important point is just because the current is fluctuating does not mean it's AC. What you're seeing here is pulsating DC. It's all in the positive direction. It never changes direction, only intensity or value or magnitude. Our diode in the circuit we are developing is going to be a radio detector, or RF demodulator. RF stands for radio frequency. We rectify the radio signal to get the audio information from the modulated RF wave, because all we need is the envelope, which is the tops of each of the tan vertical lines of the envelope, shown in black. Incidentally, you can use the negative envelope, as some circuit designers prefer to do. We'll get more into modulating and demodulating in the next video in this series as we add the diode to the circuit. I hope you enjoyed this video and found it useful. Please like and subscribe and check out other videos in this series and on this channel. Thank you for watching.